Thank you very much. Good afternoon, everyone. Can you hear me well, and can you see my slides?
Yes, it's clear with your voice also.
Good. Thank you. Then, yes, in the next few minutes, I'll be talking about our efforts to develop a new dislocation-based model to more accurately describe stream path effects in pipeline steels. So this work is the product of a collaboration between KU Leuven and OCAS, the research center of ArcelorMittal, and was accordingly funded by ArcelorMittal and the Flemish government. I would also like to thank professors here at KU Leuven for the support, and the colleagues at OCAS for their input. Now, I will start by giving a brief introduction into the spiral pipe forming process. So this is the background of the study. I will then go over to talk about different sources for mechanical anisotropy in pipeline steels. Then talk a little bit about stream path effects in these steels, and in particular about the Bausching effect, because as we will see, the Bausching effect is very large in these materials, and that is a true challenge for simulations. Then I will go through the model development and present a few conclusions in the end. So now, as you can see already here in this on these two pictures that I put here, we are dealing with large samples here. Yeah, so we are dealing really with macroscopic objects. We have here in the center some steel coils that then with a pipe forming process get formed into pipes like those shown on the right, for instance. And they can be used for the transport of all kinds of liquids around the world. Now, the challenge we are facing in this process is that we would like to predict the strength of the final pipe from the coil properties. However, it turns out in reality that this is quite a challenging objective, because when we look at the spiral pipe forming process, we see that there's in fact a number of deformations and a number of steps included, and each of them alters in fact the mechanical properties of the initial coil. So we start off with the coil here on the left, and then there are multiple steps. Finally, there's the three-roll bending step that creates the spiral shape, which is then welded into the pipe. So there are several forming steps involved, and each of them modifies the mechanical properties of the coil. And therefore, it is quite clear that to predict the strength of the final coil, we need to model somehow all these steps in between. So it is a multi-step process that we're looking at here, and we have different, not only multiple steps, but every step imposes a different deformation path. So in total, and I think you can appreciate that, we have quite a complex strain history in the entire process, which makes it a real challenge to predict the final pipe properties from the coil properties. However, to ensure safe operation of the pipes, it is clear that the pipe strength is the central property. And if we know the pipe strength, we can also ensure that no accidents occur, no spills will occur. Now, when we look at mechanical anisotropy or strength anisotropy, and in particular the strength anisotropy of pipeline steels, we can identify a number of sources which cause this anisotropy. And so these sources, they are active or they originate on all possible length scales, yeah, ranging from macro to nanoscale. Yeah? So on the macro scale, we have on the highest level, we can think of residual macro stresses. Then going a bit lower on the level of grain clusters or aggregates of grains, we have a crystallographic texture. Then the individual grains, they can have different shapes, different sizes, yeah, and these sizes and shapes, they can be differently distributed throughout the specimen. And then when we look inside individual grains, we can see, in fact, dislocation substructures. So these pipeline steels, they are mainly predominantly BCC. Yeah, have a BCC crystal structure, and it is well known that in BCC metals, when they are deformed, they form a very characteristic dislocation substructure. I will talk more about this later, but this dislocation substructure then also gives rise to macroscopic mechanical anisotropy. And then when we go one level further even, so at the level of the lattice itself, we may also find additional anisotropies coming from, for instance, non-Schmidt effects, which can be due to twinning, or also specific dislocation structures. Now, in this presentation, in this work, we focus on these two sources of anisotropy. So we focus on the morphological aspects, so the grain size specifically, and the intragranular substructure. And the goal is to include these sources of anisotropy in a crystal plasticity model, which then allows to predict the final pipe properties. Now, it turns out that in these pipeline steels, we see a very strong Bauschinger effect. So I will show this more on the next slide. I will show some examples there. But just to give a brief overview of what the Bauschinger effect is, in fact. So when we deform a material, yeah, in tension, for instance, and then revert the load sense. So then we go into compression. What we see is, in fact, yeah, that then in compression, the material yields at a much lower stress than in tension. Yeah, so there is a large stress differential, yeah, at the strain path change, and that is typically attributed to the formation of dislocation pileups at various obstacles. And these obstacles, these can be grain boundaries or also the dislocation substructure. So here on the left, this is an example of a dislocation pileup formed at a grain boundary. You can nicely see how the dislocations, how the dislocation spacing decreases towards the boundary in this pileup. And here on the right-hand side is an example of a dislocation substructure. These are cell block boundaries that formed inside a BCC steel. And also at these cell block boundaries, dislocation pileups can form and cause a Bauschinger effect. Now, when during a forward deformation, yeah, so for instance, not during tensile deformation, these dislocations, they get blocked by these obstacles, so the pileups form. But then when the load sense is removed, the dislocations can very easily move away from the obstacle in the opposite direction, and that gives rise to the stress drop when we change the strain path. Now, in the pipeline steels we're dealing with here, it turns out that this Bauschinger effect is very large. So here's on the top left is an example for a shear reverse shear test. So we have a forward shear segment and then a reverse shear segment, and we see here a very large stress drop at the strain path change. We also see that in uniaxial tension compression tests, also in cyclic tests, where we see a large reduction here in the yield stress when we change from tension into compression. In addition, these steels exhibit a very small grain size. So the typical grain size we're dealing with here is smaller than 10 micrometers. But this is already pretty fine. And when we tried to model the Bausching effect in these materials with an already existing model we saw that it was impossible. It was not able to in fact reproduce these large stress differentials at the strain path changes. So the reason for that, we believe, is that the grain boundaries in this model we used did not consider any grain boundaries. Now, so the model we had used is the one developed by Peters et al. And it is a dislocation-based substructural hardening model for BCC metals. Yeah, and so in this model we have 3 dislocation densities. There are the dislocation cells, yeah, which give rise to isotropic hardening. Then we have cell block boundaries. So these are dislocation-rich bands which form on specific 1-1-1 planes, on the most active 1-1-1 planes, in fact. And then we have polarizing dislocations, yeah, that accumulate at the cell block boundaries. Yeah, so these are the pileups which are then responsible for the Bausching effect. So during a forward loading, they accumulate at the cell block boundaries, and during a reverse loading, they can very easily move away from the obstacles and therefore give rise to the Bausching effect. Now, what we did now is we extended this model with grain boundaries. So the initial model only contained the dislocation cells, cell block boundaries, and the pileups at the cell block boundaries. Now, wishes to also include grain boundaries into this model. And in addition, at the grain boundaries, we allow pileup formation. So we introduce a new dislocation density, which represents dislocations that polarize, in fact, or that accumulate at grain boundaries. And like the pileups at the cell block boundaries, these pileups at the grain boundaries can then also give rise to a Bausching effect. So we have here sources of anisotropy that give rise to a reverse effect, to a so-called Bausching effect. But then we also have dislocation densities that give rise to isotropic hardening. Looking at the equations of that model, so I'll just briefly go over them. We have an equation or an expression for the accumulation of the polarizing dislocations at the grain boundaries. So these are not only the equations that we added to the already existing model to include grain boundaries. So this is an equation that describes the accumulation of pileups at grain boundaries. Now, when the flow, when the load sense is reversed, the flow of the dislocations at the grain boundaries is also reversed. Then we apply in that case a different evolution equation, and the entire this entire build up or recovery rate is controlled by the net flux of grain boundaries onto net flux of dislocations on the grain boundaries. Well, most importantly, we need expressions that then give us the critical resolved shear stresses that allow us then to calculate the strength and the flow stress Yeah. So we have then an expression for the critical resolved shear stress, which includes well, a constant value like a pile stress. Then we have a contribution from cell boundaries. Yeah, this is isotropic hardening. Then we have a contribution from the cell block boundaries on pileups at cell block boundaries. And then newly now we have also an expression for grain boundaries. So the grain boundaries itself, they give rise to a strength increase, and then also the pileups that form at the grain boundaries. And then importantly, if we reverse the dislocation flux at a grain boundary, that happens when the load is reversed, we see in fact that the stress is reduced. We use this equation to describe then the stress reduction. Also importantly, we have a term that describes a grain size strengthening. So at smaller grain sizes, we expect also a higher strength. Now to prove the concept of this model, we set up a simple test case consisting of a single slip system, one cell block boundary, and one grain boundary. And we assume that we have a simple shear deformation with a shear reversion at 15%. Now, so these plots here, they show, those here on the left, they show the dislocation density for two different grain sizes, and the right ones show the evolution of the shear stress for two different grain sizes as a function of the applied shear deformation. Let's first have a look at the dislocation densities, how they evolve. So we have here the four dislocation densities: the dislocation cells, the cell block boundaries, and then the polarizing dislocations at the cell block boundaries and at the grain boundaries. And so we can see that the model behaves as we would like to. Yeah, that's already good news. Yeah, so we have at a larger grain size, we have a smaller contribution from the grain boundaries than at the smaller grain size. Right, at a smaller grain size, we have much more grain boundaries, or that the dislocation mean free path is much shorter, and therefore we also expect a higher strengthening. Looking now at the shear stresses, and here it is most instructive to look at the bright blue curve, which shows the total critical resolved shear stress on this one slip system. And there we see two things, yeah, two important things, namely that if we go to a smaller grain size, if we go here from 50 to 2 micrometers, I'm sorry, then the total stress level increases, yeah, but at the same time, we also see an increased stress differential. So it increases here from 90 to 125 megapascal in this example. Yeah. So to summarize, there are two important results or effects that we see in this new model, which we also want, in fact, and that is we have the possibility to model grain size strengthening. Yeah, so something like a whole patch effect. For smaller grain sizes, we have a higher stress level, higher strength, and at the same time, we have also we see also that for smaller grain sizes, we have a larger Bausching effect. So in principle, the model does exactly what we want, and in future we will implement this model into hierarchical simulation frameworks to then in fact simulate the entire pipe forming process. So to summarize a bit, it is clear that grain boundaries play an essential role, yeah, in the Bausching effect of these pipeline steels, and we cannot neglect them when we want to simulate, when we perform crystal plasticity simulations. Yeah. And so we extended the original Peters model to include the effect of grain boundaries on the Bausching effect and on the grain size strengthening. And in fact, the newly developed model, it shows exactly what we were looking for, namely it increases the Bausching effect, and we can also see a grain size strengthening effect. So these are in principle good news. And yeah, as I mentioned, in future, we will implement this model into hierarchical simulation frameworks to then perform also large-scale FE simulations that use this hardening model to predict the evolution of the strength. I would now also like to acknowledge the colleagues at the University of Liège for carrying out reverse shear tests or in general strain path tests that we use to calibrate our model. And if you, I invite all of you to follow us on ResearchGate or LinkedIn to see the latest outcomes of this study. With this, I'm at the end. Thank you very much for your attention.